Okay, so we're going to define a term called enthalpy, which has the uppercase letter H. And to really understand enthalpy, we're going to review some of the equations we have. So we have delta E. Now we're going to say this is specific to the system now that we have been talking about the system. And that's can be changed. The energy of a system can be changed either by processes of heat or work, where we've defined work as negative P, the external pressure that can either be worked on or against the system, times the change in volume of the system. We also have heat is equal to mc delta T. And this we say is a constant external pressure. Atmospheric pressure is a really good example of that, assuming that we're not in the middle of a hurricane where the pressure is dramatically changing. So this idea, so this would be like atmospheric pressure. And in most cases, the external pressure is the same, so that's pretty real world. Reactions have this too. So something to point out here is that for delta V, if we can't have any change in volume, or if there is no change in volume, so not that. If the change in volume is equal to 0, then the work term is equal to 0. So no change in volume is a change in 0. So really what this means is only reactions in pistons or closed containers that can expand or be compressed can have W greater than 0. Or basically something that's, well, let me not say greater, let me say not equal to 0. So, and that doesn't happen a lot. If you're in any beaker, then that won't be the case. So, that's the first thing. Based on everything we've talked about so far, I'm going to introduce a new term. But before I do that, I just want to also mention something. Here, this is saying E final minus E initial. Now we are able to determine these. These are experimentally determined values. Okay, but we can't easily determine the delta E of a system because either one of these. So this is E is like E system, either final initial, is what we call the internal energy of the system. Now that is equal to basically the sum of all forms of kinetic energy plus the sums of all forms of potential energy, and these are very difficult to either measure or in most cases calculate. And so the just having E is not a very useful term because we can't actually estimate or calculate it. So need delta E because we can measure changes in this internal energy, but we can't actually measure the internal energy or calculate the internal energy either initially or finally. So that's the first part. So enthalpy, if we define enthalpy, I'm going to define enthalpy as such: H equals the internal energy of our system plus PV. Now this is not a very useful way to, so this is, let's actually write that. Not very useful. Mainly because E system, we don't know what it equals. It's very hard to determine that for the reasons mentioned above. So what's easier is delta. So what I'm going to do is I'm going to add to this delta. So if we have delta H, delta E system plus, now P and V can change, so I'm going to put the delta outside and then evaluate it through. So if we assume to have at constant external pressure, that would be P external. Then then we can bring that out front, so we get delta. We have P external. It's constant, so there's no change. Delta V, and that's equal to delta H is equal to delta E system plus P external delta V. Okay, and so this is the first equation you want to look at. Okay, equation number 1. We also can go back to our delta E system is equal to Q plus W. And so we can say that delta E system is equal to Q plus P external delta V. We've substituted in for W, but actually W is is negative. So we're gonna get this here. It's going to be I'm going to write. I'll write this to be plus negative. So W is negative P external delta V. Whoa, man. Okay, let's get rid of this. What's going on here? Okay. Plus negative parenthesis parenthesis. Sorry. Okay, that's W. So we have this expression, and now what we can do is we can say, okay, now what we're going to say here is that this is, so we can, if we want, we can bring this over. So then we get the second expression, which is Q is equal to delta E system plus P external delta V. So we just move it over. Now, this is specific for a constant external pressure. So I'm going to put a P here, and this QP equals thermal energy transfer at constant pressure. Okay, and this is our second expression. Okay, now what I want to say at this point, you're probably thinking, this isn't fun, this looks kind of hard, very mathy, and you will not have to do any of this. I am simply deriving, I'm almost there, we're almost there, but I wanted to just simply show you. Otherwise, enthalpy seems to be, we kind of pulled it out of the air when we did this first expression, but there is some meaningfulness in doing this derivation, but this is just for show. This is not going to be tested, though there will be a couple things in here that I'll highlight that I definitely want you to kind of know. So if we look at this, then we can say so this is at a constant external pressure, delta V is equal to 0. Okay, and so we can also see That's one way to look at it. The other way is that this term right here and is equal to this right here. So I can take these two and say that delta H is equal to QP. Okay, and so that's simply showing you a derivation for enthalpy. Enthalpy can be many things, but in the case in which we have a constant external pressure where there can be no volume change, then the enthalpy is equal to thermal energy transferred at constant pressure. Okay, so many reactions occur in a system at a constant pressure with delta V equaling 0. That means that the definition of enthalpy, and the way I want you to think about this, the whole reason we did this was to show you that enthalpy, delta H, or actually more specifically the change in enthalpy, is equal to a thermal energy transfer at constant pressure. So we will be looking at reactions that are going to be either absorbing or releasing thermal energy, and we can use those values to determine the enthalpy of those reactions. Enthalpy is a form of energy specific to thermal energy transfer, though it can be more expansively used to include work. In this particular class, most of the reactions are in beakers. They are not in a closed system, they're in an open system, or a system that does not allow for the delta V, such that we're only going to be looking at thermal energy transfer as a way of measuring enthalpy. So that is our little derivation, and now we're going to get into some practical applications of enthalpy, both for calculations and for determining its value.